So our speaker today for the first session in the main tracks is Cordova. Aaron is the CTO of Coverse and probably has as long of a history with Accumulo as anyone, as one of the founders of the Accumulo project. So with that, I'll turn it over to Aaron.
Hello. Thank you. How's everyone liking the conference so far? It's pretty exciting. Yeah. So I'm very excited. It's very exciting to see Accumulo come such a long way and have so many great people working in the community. So it's very, very exciting and encouraging. Today, I want to talk about one of the three things that we kind of wanted to create Accumulo to solve. Today, in the world of big data, it's very compelling, but it's also very challenging to be able to bring all your data into one place where you can ask questions and do it fast enough to where your answers are effective and timely. And it creates specifically three problems. So those problems are scale, security, and schema. You know, how do you put all your data in one place when it's all of different sensitivity levels, and how do you reason about your data when it has different shapes and sizes? But we've talked about security and schema in other places in the past, and today I want to focus on scale. So scale today is used kind of in two different ways. You hear people say things like, I'm going to scale this, I'm going to scale this up. Let's scale the cluster up to twice the original size, right? It's a transitive verb. I'm totally a linguistics nerd. You can scale something, right? Then there's the other one, scale, like, oh, my system scales, right? Which means it works even though I'm operating at a very large scale, right? So Accumulo scales. And when we talk about large scale, like, what does that even mean? So people say big data. It's like, well, what is big data? What is small data? Where does that line begin? So if you look at just a notebook computer, you can buy a notebook computer with 16 gigabytes of RAM, and like, this is half a terabyte of flash storage. You can get even bigger SATA drives, right? 2-3 terabytes on a laptop. A modern server can be had with hundreds of gigabytes of RAM and tens of terabytes and tens of cores. That's a lot of data. It's kind of a lot, right? One of the things I'm going to try to do is put all of this into perspective so we can kind of think about, how do we reason about this? So I'm going to postulate that large scale really means kind of whatever doesn't fit on one server. It's kind of a thing that people have used in the past. It's a little bit difficult even to use that definition because you can buy big vertically scaled servers with hundreds of cores, lots of shared memory that connect to massive amounts of SAN storage that's shared. But today, just using that off-the-shelf commodity hardware, the cheaper hardware, you can achieve some like really fairly, in my mind, large capabilities very quickly. So, like I said, single server. So here you can see like kind of what you can fit in memory and what you can fit in disk on a single laptop on a server, and then starting to build distributed systems. And this is kind of staggering to me. And we'll spend the rest of the slide just trying to understand, I think, this. Like, how much data is that? When do I need it? What is it like at each of these scales? So data isn't just, the reason that you need these scalable clusters is because data isn't just the data that you bring in. It's not just the data that is external, that is generated by sensors or users or any sort of observation you make in the real world. It's also all of the ways you're going to analyze that data. So it's all the results of all your MapReduce jobs. Sometimes people call those QFDs, question-focused data sets, right? So you can take a bunch of data, you can transform it, summarize it, aggregate it somehow to answer a specific business or mission question. And then on top of that, you usually want to make at least a portion of that data searchable so that people can get to it in real time. And that's kind of what Accumulo does, right? So if you organize the data somewhat by like what Accumulo does is it sorts all the keys, then you can do really fast lookups and consume the data that you need, ideally when you need it. So to build a scalable system, you sometimes you want to keep things constant as you go from low to high, as you go from small to large. And sometimes you want things to grow linearly, right? So as you go from gigabytes to petabytes, Accumulo is designed to keep two things constant and low: administrative effort and scan latency. So there's a recent benchmark that I will go into more detail in a minute that shows that as you go from 300 to 1,000 servers, you see a slight increase in scan latency. They were doing a very large number of queries per second and just dividing that number. Another way to measure, and so they were doing, they measured that each of their queries took this many milliseconds. That's less than a millisecond. Now, if you measure latency in how long does it take from when I hit enter to when I see my first result, it should also be in milliseconds, but probably not less than milliseconds. And that performance, it maintains that property as you scale from through several orders of magnitude. So that's very important, right? Because you don't want your system to degrade in performance exponentially as you grow it exponentially in size. You want it to always be fast. The other thing that scales, that works well at large scale is the administrative overhead. So in this same benchmark, they were running massive amounts of import, ingest, and query at the same time, and they saw machine failures. In a big data system, you're going to see, built on commodity hardware, you're going to see failures. And so this is the number of machines that failed, and that's the number of times they had to stop the ingest, stop the queries, and fix something, and intervene as an administrator, 0. So the system should be designed to just keep going, even though you've got multiple hardware failures. There are a lot of other distributed systems out there that aren't quite as good at this, but you don't discover it until after you've built like a 100-node system and you realize, oh my gosh, this is actually a huge pain. So Accumulo will go beyond that. And another reason that you, maybe as somebody who's trying to decide to use Accumulo, somebody who has to build something on Accumulo, the reason that you care about scale is because you don't want to hit a wall someday. You want to be able to pick a technology, use it today on a small scale, and then not have to do a massive rewrite when you scale up 10, 100x. You want to be able to keep using the system you picked and keep using the investment that you made. And so it's not necessarily that everybody needs to have massive scale in the beginning. It's more important to choose a system that can scale in the future to basically future-proof whatever you build. So there's a couple things that grow linearly as you scale up the cluster linearly. Total storage size, obviously. Double the size of your cluster, twice the storage. The ingest rate should grow close to linear, and the number of concurrent scans you can do should grow. So that means that not only do you have a system that scales in terms of the amount of data you can store, but as you get more users, or as the velocity of your data coming in increases, your system will just respond appropriately. So the same benchmark shows that as you go from, again, 300 to 1,000 machines, you get this really good, nice, linear-looking speed up. Now, it's not perfect, right? There's this thing called Amdahl's law. There's always going to be a part of your computation that is hard to parallelize, it's constant. And so you're always going to be a little bit shy of the theoretical ideal. But But, I mean, that looks pretty good to me. We'll go into more details about that now. So this was run by Booz Allen and Greenplum, now Pivotal. It's called the AWB benchmark. I try to provide sources in my slides for all these things. This was run on 1,000 machines, commodity hardware. They may have had some fast interconnects, but the disks were commodity, the CPUs, and they saw eventually 100 million writes per second at the biggest scale. That's a lot. To me, that seems like a lot, right? That's kind of a lot. At the end of their ingest, they had 408 terabytes, and a table with 7.5 trillion entries, which is pretty exciting. I'm gonna move this bad boy. There's another benchmark that came out. There's not a lot of these, but even these benchmarks are interesting. This one was I call it the graph benchmark, right? It was published by the NSA on 1,200 machines. They had a graph that they generated to run this benchmark, this common benchmark, and it generates the data for you. And what they were interested in was a graph that was on the same order of magnitude as maybe the number of connections in your brain. And so they generated 4.5 trillion vertices and 70 trillion edges. They were able to traverse, they were doing a MapReduce job to process this graph. They were reading this graph in parallel. And if you just look at how long it took to traverse the entire graph, they were doing about 150 million edges traversed per second. The total data size was a petabyte. And then there have been some other graph benchmarks that people have published. Twitter did one. I think that one was actually in memory, a billion node graph, or billion edge graph. I think it was just a billion edge graph. Then Yahoo published one. If you just go Google for these, you'll find them. I didn't put sources for each one of these, but I did for all the Accumulo ones. Facebook did one that was pretty, I think, widely read on a trillion. And it was kind of a big deal that they could do a trillion edge graph. This one was 70 trillion edges. So that's a, order of magnitude more. It's pretty interesting. So billions, right? I mean, 70,000 billion edges, 70 trillion edges. So the reason Accumulo is scalable is because it's designed after Google's Big Table. And recently, Google shared some data points that were pretty interesting. So Big Table powers hundreds of applications today at Google. They serve over 2 exabytes total, not a single Big Table instance, but in all their Big Table instances, they have over 2 exabytes that's being managed. And they serve, on average, 600 million queries per second across the entire organization. Massive, massive scalability. So those are kind of the public numbers, and I want to kind of talk about what it takes to go from 10 machines to 10,000. Now, none of the benchmarks that we talked about operated on 10,000 nodes. But we're going to talk about today kind of how to go from 10 to 10,000, and so that, again, you don't really ever have to worry about scale. That's something you never want to worry about. So starting with 10 machines, 10 to the 1. It's 1 rack. It's a terabyte of RAM. To me, that seems like a significant amount of RAM. That's pretty cool. And it's 10 to 100 terabytes of disk, depending on how many disks you put in each one of your servers. Hardware failures on these systems are actually kind of rare. Like, you may be, when you unpack the rack, you may try to turn on 10 servers and maybe one of them fails. But while you're kind of using that 10-node rack, for the most part, you're not going to see hardware failures very often. So, a lot of the stuff that Accumulo does to be fault tolerant will feel a little bit like overkill, honestly. What you can do on this 10-node cluster is test your distributed application designs. So you want to build it in such a way that whatever you build on the 10 node cluster will also run on the 10,000 node cluster without you really changing anything. So how do you do that? There's a couple kind of key things you can focus on that will allow you to do this. So one is try as much as possible if you're doing live ingest, meaning you're streaming key value pairs into Accumulo as they arrive. When you're doing that, try to use as many servers as possible, right? You want to have good parallelism, good usage across your cluster. There's ways to do that we're going to talk about. And then the flip side of that, and these two things kind of conflict sometimes, is you want to try and make it so you can do as many concurrent queries as possible. So you want to be able to do lots of queries going to different servers, and you want your queries to involve as few servers as you need to get the concurrency that you want. So it's typical to have a query maybe go to a small number of servers. Sometimes queries go to a large number of servers, but the more you can, the fewer servers involved in every query, the more concurrent queries you can do. And then finally, there's kind of ways interesting ways that I think may be somewhat unique to Accumulo for turning updates into inserts and making them much more scalable. So like I said, sometimes trying to get the rights to go to all servers and trying to have few scans per query is difficult. Sometimes they seem like they're in conflict. So I'll give you kind of two extreme examples. One is if you have information about users and you decide to hash every single piece of information about each user separately, you'll get nice uniform writes across your cluster, right? If you're using a good hash function. The ingest rate will be close to optimal. And a lot of systems just work this way. A lot of systems just take key value pairs, hash them, and send them to a server. Then when you want to get it back, you hash the key that you want, whose value you want, and you just go to the server and pull it back. So you can certainly do that with Accumulo. The problem is, and like I said, you'll get nice uniform writes. One of the things you want to look for, and these are kind of like really good numbers for bare metal maybe per server. But what you want to look for is that you have a nice even distribution of tablets across your machines. This is like a representation of the Accumulo monitor. Accumulo ships with a monitor that will tell you this. So as you're doing ingest, you can see, am I ingesting evenly across my cluster? Meaning, am I using all my hardware? Or do I have hotspots? And am I wasting resources? So you want to watch for that. The problem is when you go to do a query, I kind of did the extreme thing before, and I hashed every individual field of a user record differently, right? Which is probably nobody would do that. But what happens if you do that is you have to then kind of do really small scans on kind of a lot of servers. Maybe not extreme, but it's certainly not optimal. What I'd really like to do is when I look up a user record, just go to one server and scan everything I need all together, right? So you're getting good writes to all servers, but you're not really achieving like few scans per query. So you can kind of group data. You can design keys in Accumulo such that the data that you want to find grouped together is all kind of tucked in behind a common row ID, right? So it's a much better idea not to hash each field of each record separately, which is really extreme, but to maybe just hash the record ID. So the user ID I will hash and send all of, for example, Annie's records to server 1, right? So you see you have the same row ID for that one record. Now when I go to fetch it, I can just talk to one server, get everything I need with a single scan. Now why are scans important? So I'm talking about scans. This is how you read data out of Accumulo. You do a binary lookup on the keys, binary search on the keys. Once you found the key you want, you do a scan, sequential read from disk. It's important because seeks have not improved in performance over the last few decades very much, right? Now, if you're using SSDs, everything's different, right? You can do a huge number of lookups per second. If you're using spinning disk, which is still cheaper, you have to pay for your seek in terms of query latency. So a seek takes anywhere from 4 to 10 milliseconds, meaning you can only do maybe 100 to 250 seeks a second per disk, right? So Sequential I/O, on the other hand, has improved dramatically. So disk throughput is much better than it was 10 years ago, 20 years ago. And so if you're doing sequential reads, which Accumulo makes possible by sorting the keys instead of just hashing them, you can easily grab all the data you need and not really pay a penalty for grouping it that way. So you kind of have now a good balance between those two things. Another really hard use case is temporal keys. So if I have basically time series data and I want to put that in Accumulo, I might decide to just write it all in time order. So I get some data, I write it out. I get some more data, I write it out. I get some more data, I write it out. And the problem with this is all the writes always go to the end of the table. I'm only using one server. Even if I have 10,000 servers, I'm only going to use one at a time. So that's rough. The kind of typical solution to this is to, it is bad at writes, right? No write parallelism. But you have everything you need. If you're doing range scans over time, you get your data right away. So you get few scans, but you're not parallelizing your writes. So what some people do is they decide to bin their time series into separate little buckets, and then they write the data that way. That uses multiple servers. When I do a query, I'm going to multiple servers, as many as I have per bin, but within a bin, all the data that I want is organized. They're all right next to each other, right? So it's maybe not perfect. Again, it's kind of a trade-off between parallelism on writes and doing few scans. So thinking like this is critical to writing a really scalable application. You're likely going to run into other types of issues with different types of data, but this is the same type of thinking that you can be doing. So, and you kind of have two ways to control that. You can try and group your data under a common row ID, or you can try and split out your data by prepending kind of bin IDs. There's kind of one technique. Again, so when you want to write to lots of servers, they have to be, your table needs to be kind of split out across those servers. Splits are important when you're trying to achieve a good rate of live ingest. You can have tens or hundreds of tablets per server, maybe even thousands. Depends on the size of your servers. But you want at least every server to have a part of your table so you can write data to the entire cluster. One thing that happens is if you're streaming live data, your data may compress really well. Accumulo sorts your data, and sorted data can compress really well. And so you might be writing a lot, what you think is a lot of data, and Accumulo is just like compressing it way down. And you're thinking, why is my table not splitting out? You may need more data than you think to kind of reach the Accumulo split threshold. So inserts are fast. I should say, on a single server, you should be able to do a modern hardware, tens of thousands, maybe hundreds of thousands of inserts per second. Those are just streaming writes into Accumulo. The way it does it is really, really efficient. Updates can be made really efficient if you're careful. Update means a lot of different things depending on the context. Sometimes it just means you want to overwrite a field. Sometimes it means you want to take the existing value in a field and somehow combine it with a new value. And then sometimes you have more complex types of updates. If you're just doing overwrites, the performance is going to be the same as an insert, which is amazing. If you're trying to do just overwrites in some other NoSQL databases, the performance is not going to be the same. What that means is you're just going to overwrite the existing value, meaning you don't care what it was, so you don't have to read it off disk. Reads are expensive. So if I'm going to update the age of this person, I'm just going to overwrite it. It looks like Accumulo, from Accumulo's perspective, it just looks like an insert. So those are always fast. You don't have to do anything special. If you're combining things like appending data or incrementing data, normally you have to read the old value out, increment it, put it back in, right? You don't have to do that with Accumulo. You can actually use iterators on the server side. It's a server-side programming mechanism. What it does is it just inserts a new value next to your old value, and then when you read it, it doesn't do, so these can stream in all day long, and the performance will be great. When you read it, the iterator will combine them for you. or when you flush this data to disk, or reorganize the data on disk, it will combine it for you. So very efficient. And that, as far as I know, is, I don't know, that to me seems somewhat unique to Accumulo. So after you compact, you only actually store the updated data. Yeah. I'm going to be a little bit hard pressed. Go ahead and ask your question, and I'll tell you. If I can answer it in the slides, I'll just answer it in the slides. If these are both in memory, when I flush out to disk, it'll be one entry. If one's in memory, one's on disk, they're going to live on disk separately for a little while. But then you can do a major compaction and combine all your files on disk. And ultimately, you get one value. Good question. Yeah, iterators are very interesting. If you're doing a really complex update, like you want to read two values out from other places and combine them, you're not just sending in some new data, that you basically have to do a read, right? Correct? So these are always going to be, kind of, a lot slower. Okay, so those are some things to think about when you're architecting your application. Even if you're doing it on 10 machines, you can kind of verify that you've done it right on 10 machines, or several machines. What about these other larger scales, right? So we're going to go from 10 to 10,000 and talk about what happens. If you're planning a larger scale cluster, you might get really excited about how much stuff you can store, because you can jam like a bunch of disks into a single server nowadays. You can get like 24 or more terabytes per server. But I want to point out that the way Accumulo is architected today, that your rate of ingest is really going to be limited by the number of servers, not necessarily the number of disks per server. So even if you have two options. If I buy 100 machines, I can either have a petabyte or 12 petabytes. But my ingest rate is going to be the same, no matter if I have a lot of storage or little storage, just because the way Accumulo is limited in how many writes you can do. So the millions of entries per second is going to scale nice and, is going to scale with your cluster, but just be aware of kind of the difference between lots of storage and lots of I/O. So if you want more ingest and for the same amount of storage, you can put fewer disks in each server and buy more servers. So just be aware of that. It's actually created a model, a really complicated mathematical model. To me, it seems complicated. For modeling ingest, if you know how many machines you have and you know how fast a single machine is, you can kind of estimate what your aggregate cluster throughput is in terms of writes per second using this model. Basically what this is saying is every time you double the size of your cluster, you can expect like an 85% increase in your write rate. There's a flip side to this. People are like writing it down. That's exciting. And it's hard to. This model may break down like at the really small number of machines, but if you test it on like 2, 4 machines, 8 machines, you should get a sense for how you're scaling pretty quickly. And this has held, this model works for like clusters I built in EC2 and clusters that other people have built in different Accumulo versions on hardware, on bare metal. It's about like this. Now, I actually took every ounce of algebra that was in me and solved for n. I may have done it wrong. Some of you math guys out there want to check my math. But as far as I can tell, it looks right. Often it's not that you know how many machines you want. It's you have a target ingest rate, and you want to know how many servers to buy, or how many servers you're going to eventually have to buy. If you know your target aggregate throughput and your single server throughput, you can kind of estimate some accuracy how many machines you need. This is just another way of writing the previous model. And that constant, the 0.76 and the 0.85, I think you could try to apply this to other NoSQL databases, and you might find different constants. It would be interesting. It would be interesting to see. So the 0.85, maybe that's like the Accumulo scaling constant or something. Maybe it's determined by hardware. I don't know. So here's an example of how you can figure out how many machines you want depending on how many millions of entries you want. So you can see it's growing slightly superlinearly, right? But it's not that bad. At least the way I've engineered this graph, it doesn't look that bad. The axes are linear. All right, so you've architected your application, you've planned out how big you want to build your cluster. What is life like on 100 machines? Well, you're going to have multiple racks. You're going to have 10 terabytes of RAM. It's amazing. Accumulo caches data in RAM when it can. The latest data lives in RAM, and you can tell it to pull up data blocks into RAM for tables that are frequently queried. That's a lot of data in memory. You're going to have 100 terabytes to a petabyte of disk. You're going to have some hardware failures in the first week when you're burning in. You can expect 3 failed hard drives in the first 3 months and another 4 within the first year. So that sounds kind of specific, and your mileage may vary. But these are numbers based on a wide scale study of hardware failure that Google did. It's pretty interesting. So I'm using those numbers. So that's kind of what you can expect. So you will see some failure, right? What can you do with a 100-node Accumulo cluster? Well, you can process the entire 1,000 genomes data set. It fits in 260 terabytes. You can store and index the entire Common Crawl corpus. It's 1 billion web pages, 541 terabytes. You can store a year of Twitter, 182 trillion tweets a year. Well, at today's rates, it'll probably be more by the time you store a whole year. It's a half a petabyte. On 100 nodes, when you're in production, you're going to want to be able to scale the number of clients you have with the number of tablet servers. That's up to you. Accumulo is going to do its thing. You got to figure out kind of an optimal number of clients when you're running in production. And then how do you assign? How do you serve queries and writes for users? You have 10 terabytes of RAM, so when you start streaming data into the system, it's going to go really fast while it's filling up RAM and disk is just sitting idle. And then you're going to start flushing to disk, and you're going to find kind of the throughput of your cluster. But 10 terabytes of RAM may take you a little while to fill up if you're doing live ingest. So when you're benchmarking this guy, don't just run a quick ingest and then go tell your boss the sweet numbers that you saw, because then he's going to ask you, why did they get so bad after you got past 10 terabytes? In reality, it's not going to be. You're still writing to the write-ahead log, but when you have compactions in the background, it slows things down a little bit. All right. So what's life like on 1,000 machines? This is things are getting serious. You have multiple rows of racks. You have 100 terabytes of RAM. It's crazy. 1 to 10 petabytes of disk. So there are people operating at this scale in lots of different places. Hardware failure is a regular thing. If you use the same numbers I was using before, you're going to see failure about every 5 days. But of course, at the beginning of the year, you're going to kind of get rid of more than at the end of the year. So what can you do with a 1,000-node graph? Well, you can traverse the brain graph, right? So if you have something at the scale of the brain, of the number of connections that are in your brain, you could actually process that. People have processed that on 1,000 nodes, on 1,200 nodes. So when I say 1,000, I'm talking about like thousands, right? This is the order of magnitude that we're in. The Facebook graph, creepily, is the same size as the brain graph, right? They've built a brain-sized graph, but it's all made up of like likes and pictures of your kids and kitties and stuff, which maybe a lot of your brain is made up of too. I don't know. All the Netflix video master copies take up a little more than 3 petabytes. The World of Warcraft backend storage. You can store that. Now, they certainly don't have a 1,000-node Accumulo cluster. They're probably they have a lot of cold storage, most likely, right? They're not processing that all the time, but still, it's there. All the web pages live on the internet. Now, I don't know if this would, like, data space-wise fit on 1,000 nodes, but we're talking about tens of trillions of things, right? And we saw with the brain graph, those edges were probably really small, but we were still in the tens of trillions neighborhood, right? So you can start thinking in terms of tens of trillions of things. On a 1,000-node cluster, the things like differences between 2 compression algorithms really start to stand out. Like Accumulo compresses all the data. You may start actually really paying attention to tuning the options that you have in Accumulo. You can use range compactions to kind of help manage your data. At the end of the talk, I'm going to talk about how you kind of manage all this. You really don't want to do anything else on Zookeeper. Watch your garbage collector and name node ops. What you want to look for is your garbage collector taking longer than 5 minutes? If so, start thinking about creating a federation of name nodes, an intergalactic federation. So Accumulo 1.6 will let you actually run across 2 separate HDFS clusters. How cool is that? So Accumulo is so scalable that it outgrew HDFS. Now, honestly, with Hadoop 2, you can run multiple name nodes and share some data nodes. If you have multiple name nodes, the risk of one of those going down is higher, so you need to use probably HA name node with federation. Okay, so I'm trying to speed up because we're getting to the end. 10,000 machines, what is life like? Life is different on 10,000 machines. You have a petabyte of RAM, 10 to 100 petabytes of disk, 1 hardware failure every hour on average. You could put the entire Internet Archive in that. A year's worth of data from the Large Hadron Collider. 0.1% of all the internet traffic in 2013. All the Facebook messaging data. Facebook photos, all the Facebook photos. Maybe, high tens of petabytes. You have to use multiple name nodes. You can start looking at things like tuning back maybe the periodicity of certain central processes like Zookeeper timeout, stuff like that. You can actually combine multi-petabyte data sets, not just store them. Before we were talking about, oh yeah, I can store all the web pages. You can actually combine these web pages. You could do a massive MapReduce. You could have up to 10 quadrillion entries in a single table, in theory, all while maintaining sub-second lookups. Only with Accumulo 1.6. So dealing with data over time. Not only do you have a lot of data, but you got to actually manage this data as it flows through Accumulo. There's a couple things that everybody kind of has to focus on. One is the initial load. You already have a pile of data. You want to get it into Accumulo as fast as possible. Latency is not important. It's already just sitting on disk somewhere. Throughput is important. Use bulk loading. There's a feature called bulk loading. You can use MapReduce to build the files that Accumulo expects, load them in. What about live ingest? If you don't have a lot of ingest today, just wait a little while. Accumulo scales up dynamically online without restarting or stopping your clients. So this is the first sense of the word scale. You can change the size of your cluster while it's running. So if you have 3 servers and a bunch of clients, you're like, I got too many clients, I want to scale up my cluster. So you add some hardware, fire up tablet servers. Immediately, those tablet servers are going to start serving queries and inserts. The data is still going to be read from the old data nodes until you start writing new data or until you rebalance the HDFS cluster. Never really seen anybody do this. People tend to like build a cluster and they're like, okay, we got to scale up, and they just build a whole new cluster, and then they kind of move data over. They don't usually grow the old cluster. So not really like seen this a lot, except when I did it. So I took 20 machines in EC2, was running a MapReduce job, scaled it up to 400 machines while my MapReduce job was running. I saw multiple hardware failures, reading data out of Accumulo, writing it back. When I was done, my answer wasn't that big, so I scaled the system back down to 20 machines. I just killed off the tablet servers, but I was a little bit safer with the data nodes. I warned them that I was going to shut them down, so you can decommission data nodes. Other ways you might want to scale if you're going from smaller to really big, you can export tables, dis-CP them to your new cluster. Maybe you could use the new replication feature to replicate data. Newer data this is another pattern. Newer data is read more often. Accumulo just keeps all new data in memory just because that's the way it does it. The block cache can be enabled to keep recently queried data in memory as well. And you can, like I said, use iterators to kind of help make updates easy. If you have iterators turned on tables, you can see something like this with certain applications where you store your raw events coming in grow linearly, but the amount of data you actually store grows sublinearly because you're only keeping track of unique entities or something like that. The age-off iterator can help you remove data as it comes in. And IBM estimates, I don't know where this comes from, but they estimate that 2.5 exabytes of data are created every day. 90% of that is created in the last 2 years. That's 25 new 10,000 node clusters a day. Accumulo is doing its part to get in front of the big data trend. That's my talk. Any questions?